We are deriving relativistic mass. In other words, how does the mass change with velocity? So first off, we're going to take an object that is moving in the y direction, call that x and y, moving in the y direction at some speed u sub naught. It is going to reach a certain section right here where a force is applied to it in the x direction. So if we went to traditional ij, and we can have a k component, but I'm going to keep it in 2 dimensions. So the force is equal to some f sub x in the I direction. So the object's going to be moving in this direction. It's suddenly going to hit this force, at which point the x component of the velocity will start to increase, and then it will sort of leave that. So the dominant component of the velocity after it goes through this force is in the x direction. And we're going to call that speed v. In the y direction, it is now u. So this is before and this is after. I also want to throw in one other thing, is that u sub naught is practically 0. It's not 0, it's still moving, but it's practically 0. So that there are no relativistic effects taking place at this because of this. So it's just creeping along. It suddenly hits this and goes zipping along in the x direction, positive x direction. I know that force is equal to the change in momentum over the change in time, or dp dt if we're dealing with instantaneous, which is d px I hat plus py j hat plus pz k hat, but I'm again keeping this in 2 dimensions, dt. And that's equal to fx I hat. So this is fx I hat equals dpx dt in the I direction plus in the j direction dpy dt. So fx is equal to tpx dt, and 0 equals dpy dt. We know that this is the derivative is equal to 0, so dpy is equal to 0, or the change in the momentum in the y direction equals 0. Therefore, py initial equals py final. There's no change in the y direction. All the change, since the force is in the x direction, the only change in momentum is in the x direction. We will come back to this. We will call this the S frame. Now let's take a look at the S prime frame. S prime, so if I take my 2 frames here, I got my S frame and my S prime frame. S prime frame is going at v with respect to S. So we could write that as the velocity of S prime with respect to S is equal to v in the I direction. From S prime's point of view, we have a particle that is traveling initially that direction right there, because if I have S initially in S, it's moving like that. S prime is zipping along at v, so therefore it looks like this particle is traveling in this direction at v and traveling in this direction at some u naught prime. Then it's going to have a force applied to it, and so this particle is going to hit that and then move upwards. And so after the interaction, it's going to be moving upwards at some speed u prime. So just 2 different perspectives for the same thing. If we bring in the momentum, since momentum is mass times velocity, we have to think about the mass. So at this point, the mass is not moving very fast, so this is m sub naught. At this point, the mass is moving fast enough, so we are not assuming that the mass stays constant. Matter of fact, the mass can't stay constant. And so from this right here, we have that m sub naught u sub naught equals m times u. that in the y direction, the momentum in the y direction initially equals the momentum in the y direction finally. Here, if we look at the momentum, since there's no change, since the force is in the x direction, there's no change in the y direction. So here we have it's traveling, it's some mass m, and this is m sub naught. And so m times u naught prime, that's the momentum in the y direction before the force, is equal to m sub naught u prime. If we bring in the two momentum parts, we bring those into it, I'm basically going to divide. So I have m naught u naught equals mu. I want to get the u naughts together. So this is m u naught prime, and this is m naught u prime. So if I think about this as two fractions multiplied by each other, I have an m naught over m and an m over m naught. So basically I'm going to bring this over by dividing by this, or multiplying by the reciprocal, and similar over there. So I have m naught over m squared is equals u over u prime times u naught prime over u naught. We are left with the fact that mass over m sub naught squared is equal to u naught over u naught prime times u prime over u. Written slightly differently, that's the flip of what I had written on the previous page. So let's take a look at the relationship here, because the s prime frame is perpendicular to the movement that we are concerned about here. These are the velocities perpendicular to the s prime frame's movement, so we need to deal with the velocity transformation perpendicular to it. So I know that before, Vy is equal to u naught, Vy prime is equal to u naught prime, and Vx equals 0. So if we look at the relationship between the two, Vy prime is equal to Vy over gamma 1 minus Vx over c squared, where this is the speed, this is v right here, this is the velocity of s prime relative to s, which would be vi hat. So plugging into here, Vx is 0. So we end up with u naught prime equals u naught over gamma. And therefore u naught over u naught prime, so switching diagonal right there, is equal to gamma. So we have half of it right there. The other one, after, I have Vy is equal to u, Vy prime is equal to u prime, and Vx is equal to v. So plugging into there, so we have u prime is equal to u over gamma 1 minus the speed of s prime relative to s, which is v, the speed of Vx, which is v, over c squared, which is u over gamma 1 minus v squared over c squared. That's u prime. And therefore, u prime over u is 1 over gamma 1 minus v squared over c squared. Gamma is 1 over the square root of 1 minus v squared over c squared. So therefore, this is equal to gamma. So over here we have m over m naught squared equals gamma times gamma, which is gamma squared. Therefore m over m sub naught equals gamma. Therefore m is equal to gamma m sub naught. So the faster you go, the greater the mass gets, because remember, gamma starts out at 1 and gets bigger as you get faster. So mass will start to increase, and this is why if you apply force to an object, it has an acceleration, F equals ma. As it gets faster and faster, the mass increases, and so the acceleration will drop, and this is why you will not exceed the speed of light if you start lower than the speed of light. At least it's the math explanation for it.